Anders' talk, the previous talk, was amazing as a survey of machine learning. I had included some overview of machine learning, but I'm going to skip through a lot of that because I would not do it justice. But I did want to talk about what's going on with Spark with respect to machine learning. It's interesting because we're trying to look at what can be done at scale. So I had some background. I will throw out this pointer. I think that this is actually, if you're not familiar with machine learning concepts, this is a fun introduction because it's very interactive. It's a nice progression. It's kind of machine learning in one web page. So I'll leave that up there because I think it's got some very good examples and visualizations. In terms of what's in Spark, I'll go through the MLlib library and talk a bit about why it's there, what the goals are. But primarily, we're looking at really two kinds of types of modeling, one having to do with convex optimization models, and the other having to do with matrix factorizations. Anders had a richer way to break this down, and frankly, Spark hasn't implemented all of the ways that he was showing. It's really focused on these two mostly. In terms of convex optimization, the different linear models, support vectors, different ways of putting together classifiers, etc., will tend to fall into this. And as mentioned, you work with your training set, your test set. You optimize your classifiers based on the training set, and then evaluate it based on the test set. And that's great if you have the classes. If you don't, then you may need to do some type of unsupervised learning to try to understand a bit more about what's in the data. What is the structure of the data set that you're working with? And there are different matrix factorization techniques for this. Typically, you'll be working with a covariance matrix of the data and peel off the eigenvectors, finding the corresponding eigenvalues to explain the variance in the data. And use those to perform dimensional reduction. I know that that's a super oversimplification, especially based off of what Jeffrey Ullman was showing with some of the different kinds of edge cases that you encounter in clustering. But this is the general thing that you're doing. One thing I'll point to, one of the things, I studied machine learning at Stanford over 30 years ago. And Jeff Ullman was one of my professors, actually, at the time in the grad program. And I was under Doug Lennett was my advisor. And he was actually having troubles at the university because at the time they were not accepting a formal definition for machine learning. It wasn't yet embraced by academia. And one of the problems is that if you look at the history of what's gone into machine learning, early on there were people working in control systems, really. And then after that, people working in biology. Norbert Wiener brought in some of the early neural network people to McCullough and Pitts into MIT. And then from there, you saw people from symbolic logic and other people working in areas of electrical engineering, really, a lot of information theory, and on and on. So these different fields have all contributed to machine learning, but they tended to have very different kinds of descriptions for what they're doing, very different nomenclature, and also relatively different math. And so I think that if you look at the field of machine learning and try to look back at the history, it doesn't align very well because it comes from all these different disciplines. At the end of the day, most of them are doing some type of optimization, some type of generalization by optimizing a model. One thing that I'll point to that I like very much, Pedro Domingos from University of Washington has a great paper that looks through the different areas of machine learning and tries to draw some general categories of what's going on. That's kind of a pun, actually. That's what machine learning does, is to draw some general categories. But the thesis there is that we're working off of a type of generalization. It's based off of representation, coming up with your features, something that's computable representation, and then building the learners, optimizing the learners, and then from there evaluating the models that come out. And so he's able to take all these different disciplines that have contributed and align them in this way. So I definitely recommend that. My view of it, I've led data teams for a number of years, and we tend to have a workflow. This would be sort of an ideal workflow that we see over and over. And the idea is that you're bringing in your data. You've probably got some large unstructured data. If you're working in big data, you're probably going to join that with some more structured data, profiles, user profiles joined with logs, say. And you're probably using some kind of metadata to align those, to be able to do the joins. But at the first part of your pipeline, you've got a bunch of ETL, and you're going to get your data sets together. And that may be big data, but by the time you joined it and cleaned it up, it may be small, as Anders was just saying. If you read some of the earlier descriptions of data science by, say, DJ Patil. If you've ever read, I believe it's Data Ninja and Building Data Science Teams, he makes the point that you spend 80% of your cost just doing data preparation. And as soon as you've gone and produced models and start to bring in other varieties of data, or as soon as your definitions change, and you dig deeper into the data and come up with better questions, then you're back to the point of preparing your data again to iterate. So you spend a lot of time in data preparation, and usually the goal there is, number one, exploring, finding out what kind of structure is in the data. Some type of reporting, some type of visualization, and a lot of projects don't go beyond that. At least in industry, this is what I've seen, is that in a lot of times businesses will just want to get to this point and run their queries and come out with the metrics that summarize, where's the most valuable customer, that kind of thing. But if you do move on in the workflow, the next step would be to do some type of feature engineering. And that's a hard problem. And what I was trying to show in this graphic here is that the harder parts are in red. And really to echo some of what Anders just described in much more detail, understanding what type of algorithms to use for the models is not really as important as, in my opinion, these three areas that are in red. So exploring the data, being able to understand really where the structure is, that's the hard part. And it usually requires some domain expertise. You can't just be given a raw data set and expect to understand it in depth. Doing the feature engineering is also a very hard problem. We do have some great tools now in terms of being able to help develop or being able to help featurize your data better. Deep learning, of course, is very, very popular for this aspect. But really, a lot of the use cases for deep learning are primarily to come up with better features, at least in my opinion, as I've seen it. There's other things that do this as well. I think that actually Anders had shown about genetic programming and had started to mention about symbolic regression. I believe that there are some areas of like nonlinear optimization, symbolic regression, which is also relatively good for exploring feature vectors. And I don't think that area has really been pushed as far as it could be right now with the given compute. Once you've trained models, there's a lot of optimization. And once you have the models in hand, the hard problem then is to be able to evaluate them. And really understanding what type of evaluation metrics fit the type of learners that you've used, the type of algorithms you used, that's also a hard problem. I think a lot of mistakes I've seen in industry because people didn't understand the evaluations clearly enough. I had one CEO who had taken statistics classes, and he told me it all meant everything in statistics was defined by R, what the R squared value was. So anytime we brought any kind of analysis, he wanted to know what the R squared value was. And until we could tell him that, he wouldn't listen. And we tried to tell him, that only works for linear models. It doesn't really work for the other stuff. Now, another thing I'll point out is that looking at this type, again, going back to Pedro Domingos, he talks about representation, optimization, and evaluation. And another thing I just want to throw out, since we're a lot of the emphasis of the program here is about building teams and doing projects, a model that I've used on data science teams for building large-scale machine learning apps is this right here, where you really take and analyze the different phases of what you're doing in your project development versus the type of skills that are required, and try to see if you've got coverage. And I think that this is a visual way of representing the problem of data science in the industry, because you can probably find people that understand the systems, how to run Linux servers, and you can probably find people who understand how to do SQL queries, but trying to get coverage across the different parts is actually a hard problem. I can talk about that more, but I just thought I'd throw that in because of the team building aspects. Another thing is trying to understand where is the relationship of people and automation, because as we're building machine learning pipelines at scale, building workflows inherently mean people and automation, not just automation. And I think that this is often overlooked when we're talking about algorithms. But realistically, there are points where people have more touch, and then there are places where there's more automation. But there should be good handoffs and good dividing lines between them. Another thing, when I go back here to this diagram, when we look at the optimization phase, what's interesting is if you pull a cluster trace from, say, Google or Twitter or Facebook, and you look at what their clusters are running, there's a lot of gradient descent, really. If you peel off the data movement and you peel off some of the known things that you would suspect that the computers are doing, they spend their time doing gradient descent or something like that, some type of optimization. And what's interesting is, anybody here seen ADMM? Some? Okay, great. Yeah, excellent. So this is part of the rhyme and reason of MLlib in Spark, is that there has been work for the past few years out of Stanford and others, but this is Stephen Boyd and Neil Parikh at Stanford. They have shown that they can take a pretty broad range of different machine learning algorithms and specify them as a convex optimization problem. So if you think of a machine learning algorithm as being a loss function and some type of regularization, you can come up with an optimization problem to characterize that. And then given a data set, you can take and optimize for this. They're using alternating direction method of multipliers, alternating descent. So what that implies is that some of the problems in machine learning, classically, at least the model selection, can begin to look more and more like a compiler problem. We can start to automate parts of this pipeline. And so that's why Spark went to work on what's called MLlib, because we do believe that by having better pipelines and better metadata descriptions of what you're trying to accomplish overall in the workflow, then you can start to do some of these more advanced techniques. And this project in particular informed MLBase, which was the parent project for MLlib. So for MLlib and for other machine learning work on top of Spark, I'd reference, there's a few points here that I'd point you towards. Number one, Joseph Bradley is one of the lead committers on MLlib and now ML pipelines. He's at Databricks, and he had a pretty good survey of this at Spark Summit recently, so I'll definitely point out to his talk. There was also a MOOC that it's called Scalable Machine Learning that Amit Talwalkar just presented that started the end of June. And Amit had written MLlib, that was his PhD thesis. Amit's partner, his research partner in the grad school, was Evan Sparks. And Evan had initiated a lot of this by coming up with a project called MLBase. And part of MLBase really was looking at techniques like ADMM to optimize pipelines. So the way that this works is that Amit's work, MLlib, is basically building blocks for what Evan Sparks was looking at more in the long term. I have a few other links here that I'd recommend. Number one, though, definitely Reza Zadeh is a professor at Stanford. He's in the ICME computational mathematics department. And he's also one of the lead committers on MLlib, and particularly with respect to clustering and work with large matrices. Very interesting work there. Hossein Falaki is also another one of one of my colleagues. He was formerly a data scientist on Apple Siri, and he joined Databricks last year, and has also been contributing a lot on Spark R, but with respect to machine learning. So that leads up to MLlib. The idea of this is there is a difference between a framework and a library. There are a lot of different types of very good machine learning libraries, and you can point to like Vocal Rabbit if you're working in C, or I don't know, H2O or Mahout, et cetera, et cetera. The notion of MLlib is to create building blocks for kinds of pipelines that could be optimized. And so it's more of a framework. It's more of the matter of having applications apply pressure on a framework to understand how should the API, how should the framework change to be able to accommodate the applications at scale in industry. So MLlib is not positioned to be a general purpose library. It's positioned to be building blocks that other things that are more general purpose build on top of. The three things that MLlib is going after are, number one, to leverage scale, in particular, working with learners at scale. Having done a lot of machine learning projects on Hadoop, the typical approach is that you sample your data, train it on a single node, and maybe an R, and then externalize that as serialize it as PMML or some type of representation, and then you can do the scoring part of your apps at scale with Hadoop, but you probably don't do the learning parts of your apps at scale. At least it's not as common. With Spark, one of the things that they were trying to do was really to go after learning at scale. And that was a very early goal for Spark. Of course, trying to leverage parallelism, but more importantly, trying to leverage the kinds of sparsity that we tend to see in these applications. Particularly when you're working with representations in large matrices, you probably have some kind of sparsity. For the components that are in there, there are some column-wise statistics if you want to find out the mean, max, min, et cetera, et cetera. There certainly are different linear methods for regression, different types of classifiers. There are some collaborative filters built in. ALS, alternating least squares, is one of the more popular ones of those. There's a few different methods of clustering now, but it started out with some variations of k-means, k-means plus plus, or k-means pipe, different optimizations off of k-means. In terms of factorization, I'll show some examples, but there's principal component analysis, singular value decomposition. There's been some other work that's been added. Reza Zadeh's team in particular is really pushing that. More recently, though, the later releases of MLlib have been about the building blocks. So being able to have sort of hyperparameters for your pipeline to be able to describe different ways to do feature extraction, different ways to change up the normalizers, change up the optimization that's being used, et cetera. And some of that actually crosses over into GraphX, because there may be, like Gibbs sampling, there may be reasons to be doing graph work. Yes?
So is it a library and a framework?
Well, Spark is a framework. MLlib, I mean, it says lib, so it says library. It's more of a library for a compiler than for a human, I think is probably a good way to put it.
It does have classifiers and
Yeah.
clustering methods and these kind of things.
Yeah,
you use as a library.
You can use these, although what I do see in industry, I mean, to be fair, when I look at the large companies that are doing large-scale deployments with Spark, a lot of them have rewritten their own their machine learning libraries. They may use parts of MLlib, but they generally implement what they want. So if you look at Intel and Huawei and just kind of going down the list, they have their own views on what they do or don't want, whereas MLlib is more of like the roadmap of what the framework is trying to understand. So it's a little bit of research mixed in with the production. Is that? And also this is being rolled out in stages. So MLlib has been used, but now there's something, there was something being called SparkML. It's now kind of morphing into being called the ML pipeline. And as an example, this is from Joseph Bradley, showing how to set up an example pipeline, in this case for logistic regression. The idea is that you've got some type of feature representation and and then more advanced work on feature representation, some type of model that you're building, and then some type of evaluation. So there's this classic pipeline that's described. By virtue of the functional programming with Spark, you have a very concise definition, as you can see up there. And this also allows, again, because of the lazy evaluation in Spark, this does allow some opportunities for optimization. The compiler can do some pretty interesting tricks there. But more importantly, I think that with Spark, the real message there is about workflows overall. So as opposed to using a very highly tuned, I don't know, say H2O or some type of library that has a lot of rich features, Spark is emphasizing more of the workflow. So going all the way back to the source data. And how can you do some interesting optimizations all the way across? That may include your ETL. It may include pushing predicates down into your frameworks that you're drawing your data from. Okay, so as far as machine learning, I can give a flavor of this. If you look under Spark Camp on Databricks Cloud here, I'm going to just show this quickly, but I'll leave this as a exercise if you want to check it out. Reza Zadeh and I both took a pass at this, and we came up with a couple of versions of this. But is everybody here seen the Iris data set before, mostly? Okay, so if you haven't seen Iris, about 80 years ago, somebody looked at, I think it was a plot in Africa, looked at 150 examples of 3 species of iris and made measurements about the petal length and the width and the sepal length and the width. And so there's this database that it's pretty small, and it has 4 features, and then a label, the species. And so it's fairly compact, but it's extremely well known. And the interesting thing is that one species is very distinct from the others, but 2 of the species tend to overlap in terms of how they're described. So this is a great small data set to use. For instance, if you use a linear classifier on this, it'll probably get confused on the 2 species that are overlapping. Whereas if you go and use something that has ensembles, maybe like random forest, you'll get much better performance. So if you want to do Iris database with Spark and MLlib, here's a few things that Reza has used. First off, we'll take the Iris database. We've imported it from R. And actually, we're working in Scala, but we pulled the R version of our Iris database. And we'll take and vectorize, basically pull out the sepal and petal features per flower. So we're creating some dense vectors here. Now we can go and just take a look at basic stats if you want to look at column-wise stats on this. So, here's the mean, looking at L1 and L2 norms, variance, etc. But let's go in and do some kind of modeling. So for instance, we could do k-means clustering, in which case we'll take, let's see, we've got the vectors right there, the data, and the parameter k, we'll set to 3, because we know there's 3 species, and give it some number of iterations, in this case 20, and we'll come up with clusters. And then we can evaluate how well did it performed. For most of the models here, we do have some type of metric, depending on the type of model. With k-means clustering, a good metric to use would be within set sum of squared errors. So that's built in here. You can print that out. And roughly 79%. Okay, so it did okay. Other things that we could do with Iris, we could take a look and instead of looking at this as vectors, we could basically construct a matrix out of all those vectors. So we've got a row matrix, a way of defining row matrices in Spark, although there is current work to move into block matrices, which are more efficient at scale. But in terms of row matrices, very simple to describe that here. Basically just wrapping the RDD that we had for the vectors. And we can get some numbers out of it, see what dimension it has. But once we've got it as a matrix, then we can do some of the matrix factorization methods. So for instance, PCA, we'll take a look at principal component analysis, pulling off the top 2 principal components is just one call. And from there, we can get basically the transformation. This is actually a criticism of Spark, and I've had this criticism of the people who wrote it. In industry, when I'm using PCA to explore a data set or maybe do some kind of projection into a lower space, I generally want to see the eigenvalues as well as the eigenvectors that are coming out, because I want to know where to make the threshold cut, where to decide how many principal components to select. And the professor who implemented this said that that's not needed. He said it's not needed. So, yes, talk to Reza. The one criticism I have here is that there's no way without rewriting this class to get what the eigenvalues are. You only get the eigenvectors. Which I think is kind of silly, but sometimes it helps to have some industry experience. I'll leave it at that. Okay, but other things. So PCA is really useful. It's akin to clustering. If you take a sample of your data and run PCA, you can start to get an idea of really how many clusters possibly would be in there. Theoretically, that's not exactly correct. So the theoretical computer science people will probably tell you no, but practically, it's a great technique. And so PCA is also useful, say, if you wanted to take a high dimensional space and then visualize it in 2 dimensions as a scatter plot. There's a lot of different kinds of uses. Another type of matrix factorization would be to do an SVD, a singular value decomposition. And Jeff Ullman had shown this, so I'm not going to go into detail, but it's a way to dial down the resolution of your matrix, if you will. And so to do an SVD in Spark, very simple. We've got the row matrix here, and we're just going to do this one call to compute SVD. And then from there, we've got U and the singular values and V. On and on and on, more of these. But I'd like to develop a little bit further and talk about graph analytics, because I'm going to show an example that will combine both MLlib as well as GraphX. So one thing is that a lot of real-world data can be represented as linked data, as graphs. And you see this in industry over and over again, whether you're talking about sales, marketing funnel, whether you're talking about supply chain, a lot of different types of social interactions, of course, bioinformatics, a lot of applications are graphs. And generally speaking, if you've got a graph, you can take and find an adjacency matrix or a transition matrix, depending on the type of graph. You can create a sparse matrix out of it. So there's a nice bridge between what you're doing with graphs and linear algebra. And we were having this discussion at lunch. It's kind of interesting to look at Silicon Valley because Facebook was out earlier than Twitter, and Facebook had a lot of funding. And they also make a lot of money off of the amount of data that they bring in. So when they realized that they had this huge, enormous graph problem, they helped use and extend Apache Giraffe, and that's a big investment, doing the graph analytics at scale, at Facebook scale. When Twitter came along a few years later, they didn't have as much money, and they didn't have as much revenue based on the amount of data points that they had. So they couldn't really afford to do that. So instead, they took the philosophy of taking their complex social graph and creating matrices out of it. And then they built very highly optimized matrix libraries on Hadoop in Scala. It's something called scalding. They built this so that they could do this approach, shift the graphs into linear algebra and optimize on the linear algebra side. So if I have a graph like that, I can take and represent it as a matrix like that. And I think that Jeff went through this in a lot of detail. Once I have that kind of matrix, I can do some interesting tricks. I can use the eigenvalues to find out things like what's the diameter of the graph. So you can go back and forth and have some very, very nice effects from that in terms of optimizing the math. And by the way, if you ever want to get a really good view of different types of sparse matrices, this is from University of Florida, and there's a particular researcher there, Tim Davis, that has a museum of sparse matrices. And for every different one, there's like a MATLAB code snippet that'll render it. And they look like alien life forms, but it's really useful. You can use this for testing your algorithms. So if you want to see the museum of sparse matrices, there you go. And also, there's a great book that's just coming out now. Richard Brath and David Junker from it was a company that had been called Oculus Info. It's now being called Uncharted Software, but they do a lot of streaming at scale in the U.S. Well, they're actually based in Canada, but they do a lot of work in the U.S. And I've done some work with them. They use Spark streaming, but they do some incredible visualizations of graph problems. And the other thing I'll say about this is that if you have a simple graph, you can do these techniques to shift the graph into a matrix, like we do in Spark. But if you have a more complex graph definition, for instance, if you have different links between two nodes with different kinds of attributes on them, then you're no longer working with the simple graphs. Instead, you're probably starting to look at some type of tensors to define your problem. And of course, tensors are very useful in astrophysics and other areas of science and research, but they're notorious for being difficult to work with, and there hasn't really been a good general purpose tensor factorization library. But we are recognizing, as we're working with large-scale graphs in projects like Spark, that there's a need for this. And I've heard this from several large customers, that it would cut down a lot of the code they have to write because it would be more of the general case. So I've seen at least 2 projects, and there is one we were talking about at lunch at Google as well, of having a more general purpose tensor factorization. Anima Anandkumar at UC Irvine, her team is actually building this on top of Spark, and they do a probabilistic approximation of a graph to fit a known tensor solution, and then do the factorization. David Gleich is at Purdue. He was previously at Stanford, and he's working with a team at Stanford and UChicago on similar things, using random walks to be able to do tensor factorization. I highly recommend watching that space. I think that that's some of the most interesting parts of big data currently for research. Given that, I'll talk a little bit about GraphX. GraphX is a project that came out of, number one, there was some work at CMU that later became GraphLab, and now there's a company called Datto based around this. Joseph Gonzalez, one of the principals on that, had been doing a postdoc at Berkeley, and he implemented the GraphLab API on top of Spark. There was also a paper called Pregel that describes how Google does its very large-scale graph infrastructure, and somebody else had implemented Pregel on top of Spark. So these 2 projects came together into something called GraphX. And this will work with the category of problems that are called graph parallel systems. It indicates whether or not the problem could be solved in parallel at scale by GraphX. Also, we want to stress the importance that it's not just about the graph algorithms, it's about the whole workflow of data feeding into it and also the usage downstream, and trying to optimize across the whole workflow. And here's some great sources. There's the original paper from GraphLab, and also the original published paper from Pregel, and some interesting discussions about GraphX. Ankur Dave is the current lead or graduate student on the project. So in terms of GraphX, the idea is pretty straightforward. In Scala, if I take and define a case class to describe the kind of data that I'll have on a node in the graph, say I've got a graph of people, and I know their ages, and I know some sort of connection between them. So I'll create a case class here called peep that has the name and age, and I've got an array of data, and then I've got an array that describes the connections between those nodes. In Spark, the idea is to create an RDD out of the nodes, and then an RDD out of the edges connecting the nodes, and then take those 2 RDDs and compose them into a graph. So now you've got the type signatures. Again, this is Scala. So you've got the type signatures for the type of data at the node and the type of data in the attribute on the edge, and that's the type signature for your graph. And then you could start to apply functions to the graphs, and the result sets that you get back from applying those will be RDDs. So there's a very nice tie-in between what you would do in Spark, whether it's Spark Streaming or Spark SQL or any of these, and how you manipulate graphs. In this case, it's a very simple traversal. We're just going to take a look over the triplets. We're going to look over an edge and the two nodes on either side of the edge and apply a filter. I could do something more complex, though. So a lot of graph work is really focused more recently on social networks and the kinds of things you expect to see at Facebook or Twitter, Google, etc. But historically, a lot of graph work has been used for optimization in industry. So for instance, imagine that you have a graph like this. Maybe you've got 4 airports, and you're looking at the cost to go from one airport to the other. And you want to try to minimize the cost on a route. So if I take a look, I'll show implementations for both of these in GraphX. If you go under SparkCamp 08 GraphX, the first one is right here, is a very simple graph of people, their ages, their names, and their connection strength, and just running a filter on that. So you see I've composed the two RDDs into a graph G, and then I just run the filter, and it comes out with the two results right there. It's a very simple traversal. But if I want to do something more complex with the graph, for instance, everybody here familiar with Dijkstra's algorithm? Okay. So an implementation of that in Scala. Right here, I'll have that graph that I'd shown of 4 airports, and I have the edges that describe the time and distance between them. This is not exact times, but just some dummy data. We'll take and parallelize the node and the edge and create RDDs and compose them into a graph. And now we'll take and create essentially a shadow of that graph. And we'll basically say that we want to look at vertex 0, but all the other, node 0. All the other nodes, we're going to set those to infinity. And then we'll take a look at the cost between them. So the implementation of Dijkstra based on Pregel in Spark is right here in Scala. It's just a few lines of code. Basically, we're going to do what's called a single source shortest path, and we'll start at one node and look at the cost of getting back to it through different paths. So if we run that, we see that to get back to node 0 is trivial from 0. Of course, there's a 0 cost. To get back from node 1 is a cost of 2. From node 2 is a cost of 1. And from node 3 is a cost of 2, but with a slightly longer path. And so, this is the kind of thing that Google Maps does when you're doing Google Directions. This is the kind of thing that FedEx and UPS and DHL and all these kind of transportation companies, they do this all day, every day. So routing problems are pretty common. Yeah?
If you like to use a vertex-centric programming model in GraphX, and then do we need to use the Pregel API or we have other options?
There are a few ways. That is one thing that's still kind of in flux with Spark and graphs, is that there are usually a few ways to do everything. The high-level APIs have stabilized. The low-level are still being optimized, so they'll tend to be in flux for the next few releases. I would recommend doing it in Pregel because it's much more compact.
The Pregel version of Spark.
Yeah, Pregel.
I meant that.
So for instance, doing PageRank in Pregel is like 5 lines of code. It's a very compact representation.
I wonder if there is another solution or
Yeah.
that's the only way.
No, you could do this in other ways. I think that with PageRank, I've played around doing there was 4 different implementations. You could do something naive, you could do something based off matrices. There's a lot of different ways. So, yeah. But probably Pregel is best. Okay, so we've seen about some MLlib, and we've seen about working with GraphX. So I want to show an implementation. Anybody here rent bikes, like live in a city area and rent bikes in Metro? I'm going to use data from Washington, D.C. I live in the Bay Area in California, so of course we have a bike share like this also. But this is one from D.C., and they make all of their data open. So it's a very interesting data set. It's got some time series aspects. It's got definitely some linked data, right? Geospatial. It can be used for a lot of different things. So this is under a folder, Spark Camp Bike Share, if you check this. And this will be looking at all the rentals during one quarter in downtown Washington, D.C. And so the bike set, here's the link if you want to download the raw data. I've loaded it up into the cloud already. But it has trip duration, start time, end time, start station, end station. It also has the ID of the bikes. The individual bikes are known. And it has some metadata about the members. And this is all CSV. And the code that I'm going to show, I've put up on GitHub if you want to grab this. And if you want to take a look at Google Maps and kind of explore that, here's a shortened link for it. There's basically the area. Okay, so at this point, actually, let me cut over into the notebooks, because I think that's a better way to look at it. So if you go to right here under Spark Camp Bike Share, right here at the top. Come on. All right. So I just wanted to display what did these trips look like. Here's the 4 quarters of 2014, and the data is not huge, but it's an interesting size. Given that it's a graph, it's probably more than I'd want to do on my laptop.
Is the number like 100 megabyte or 100
Yeah,
megabyte or something?
Yeah, gigabytes. It's not huge, but again, this is just for the downtown area in one year. It'd be interesting to go. They have a lot more data, more historic data. I'm going to create. Is this readable? By the way, is the font size? We'll make it bigger.
So,
Is that okay? Good. I should have done that before. So we're going to take and read this in as an RDD. And if you look at the raw data, it's kind of what you expect. It's comma-separated data, so it's a little hard to read. I'm going to create a couple of functions here. One is called convert duration. The timestamps are given as strings, so I'm going to convert those to a long, so I can get something numeric to manipulate. I'm also going to define a case class called trip to represent one bike trip. Again, as an object, instead of taking this as a tuple, I'll take it as a case class. So here, I'll take my raw data and I'll split on commas to create tuples, and then I'll filter out the header line, and then I'll take and map the tuples into my case class. And while I'm doing that, I will convert the timestamp into the duration timestamp into numeric. And then from there, I create a data frame. Because again, data frames are really a higher level way to manipulate data in Spark. And I'll register that with a catalog. I'll call the table bike share. And from there, I can run queries against this. So you can see just randomly, if I pull up some bike trips, I can see the different stations where people are renting the bikes and then driving the bikes to and returning them. Let's see here. Okay. Now, one thing that I think is interesting is when you take a look at the durations, there's pretty good distribution on the durations there. But one of the things I noticed looking at this data is that the registered users are divided into 2 classes. One class are the people who've paid for a registered account, and the other class are tourists, people who just pick up a bike and go ride it for a little while. And this is Washington, D.C., so if you've how many people have been to D.C.? Anybody here? So anybody ever been there during the cherry blossoms, like during the spring? But it's really beautiful. There's some areas there that are incredible during spring. During the winter, not so much. But during spring, it's highly recommended, and it's a popular tourist site. So one of the things I noticed, taking a look here, was that if you take a look at duration versus class of user, let me get back to this. If you take a look at that, you've got a pretty interesting relationship there, that the registered users tend to go on pretty short trips, and the variance on the time for their trips is pretty tight. The casual users are tourists, and so they go out and they ride their bike to a tourist site, they take some pictures, buy an ice cream cone, and they spend a lot of time. So that's an interesting relationship right there, and I thought, okay, well, let's build a model and measure this. Maybe we can actually predict this, and we could use that for, I don't know, marketing, maybe ads or something like that to the people on bike trips. So here in Spark, what I'll do is basically prepare this data to create a machine learning model, and then we're going to go and approximate Google directions. So first off, I'm going to take a look and grab all of the unique names of bike stations that are represented in the data. And so I'll map this and just pull out the stations, both the destination and the source, union them together, distinct to get the unique ones, and then I'll call a function in Spark called zip with ID. So I've got the name of the station and a unique integer. And I'll collect that as a map in Scala. Yeah, and then that just looks like a map. You can see the name mapped to the value. And now I'm going to go through and do the featureize part. I'm going to create the feature vectors because I want to build a classifier to try to take a look at the duration at a given station, the duration of the trip, and then try to predict whether or not it's a registered user or a tourist. So here I'll create some vectors that have been in lib. The vectors, we're actually calling this labeled point. So I've got the vectors of the dependent data, and then I've got the label. In this case, it's very simple. The dependent data is just the duration and the start and stop, and the label is the class of how the user is registered. Okay. So now that I've got those, I'll take and split this into a test set and a train set. I'm going to say save 60% for my training set and save 40% for my test set. So I'll do a 40% holdout. That's kind of big, but it's fine for this. And so now I've got 2 data sets there, test and train. And I'm also going to keep track of how large the test set is. I'll use this later. So actually, coming right off of what Anders was showing, I'm a real believer in using naive Bayes. If you haven't worked with the data before, going in with a technique like naive Bayes to try to understand what's really in the data. Because naive Bayes is very transparent. You can understand why it's making the judgments that it's making. So it's a great first step. It's not exactly the best predictive kind of model, but it will give you a lot of valuable information. And it doesn't have many parameters, so you can just jump right in and do that. So I'll create a naive Bayes model, training it here, and then I'm going to evaluate it with a test set. So I'm going to come in here and I'm going to take the test set and map it. And for each vector in the test set, I'm going to call model, predict on the features, and then compare that with the label that's expected. And I'll get back essentially this other vector of the results. And then what I'm going to do is count those and put together what's called a confusion matrix. I'm going to count how many times true evaluated to true, how many times false evaluated to false, how many times true evaluated to false, etc. So I look at my false positives and my false negatives. I create a matrix out of all these. And I'll just save that as a Spark, as an RDD. So now I have my confusion matrix for naive Bayes. Overall, it showed about 73% accuracy. So I could predict if somebody was a registered user or not just by looking at where they were going and how long they took. Okay, so let's try this with logistic regression. Here, same kind of thing. It's a different algorithm I call, but in the same way. Take my training set, and then I collect my confusion matrix. I've got confusion matrix LR for logistic regression. And then down here, let's see, I'll take and do decision trees. So a decision tree is, a way of building a nice classifier. It takes a few more parameters, and you're using a different way to approach the data. Instead, you're looking at the information gain by branching the tree. But I can still describe the results as a confusion matrix. So I've got a confusion matrix decision tree. And then down here, let's take this a little further. If you take and create a lot of trees, you can create something called a forest, a random forest, which is to say it's using a technique called bagging, bootstrap aggregation. We'll take the data set and pull most of it, but hold out part. We'll create a decision tree off of the part that we sampled, and then we'll evaluate it with the part that we held out. And we'll put that tree in the forest, and then we'll repeat and just keep going on and on. And when you get done, you actually know how much error there is in the model because of all the error that you've measured as you're building the trees. So random forest is an excellent technique that I tend to use a lot in production. So here I've got confusion matrix random forest. And by the way, I don't know if you've noticed, but the rates are improving. So here with Spark, I'll take all these four models here and put them together in one big matrix, and by doing a union right there, and then we'll just display what kind of error they have. So you can see that if somebody is a casual user, you can see what kind of rates. As it turns out, logistic regression here didn't do very well compared to the others. Naive Bayes does very well, and the two different tree structures are comparable. If you look at the case where you have a registered user, this is interesting. Naive Bayes, it does pretty well. Actually, logistic regression does really well, and they're all fairly comparable. But what's really telling is when you get into error cases, and this gets back to some of what Anders was talking about. If you look at the case where you've got a false positive, you can see that logistic regression is just like off the map. So logistic regression performs very poorly when it comes to the error cases, which is what you'd expect if you have some noisy data. And similarly over here, well, it does pretty well in this case for the false negatives, but for the false positives, it had a real problem. So there's trade-offs there, but generally speaking, at scale, we're probably going to see random forest outperform logistic regression if you have a lot of variance in the data. And it's an ensemble. You would expect this to happen. One of the problems that I've run into in industry is that the executives, the product managers, and the executives usually go to business school. And in business school, they usually have economics professors. And economics professors love logistic regression. And so they'll tell everybody, use logistic regression. That's how you get CEOs who come back and say that they want to know what the R-square value is. And so you're trying to go in and show the product managers that logistic regression is a really bad idea if this is how much the bank is going to charge us because of fraud. And I've actually been in that case where I could show them the graphs and they said no. So keep that in mind. Okay, I'm going to move on. I'm going to take this data and store it out. Let's do some graphs. So I want to take a look at some of the trips. And how are we doing for time? We got about 10 minutes here? Good.
Yeah, 10 to 15.
10? Okay, we're right on schedule. So I've just got some raw data here for different trips that I've pulled. But I just want to show you what the raw data looks like. Down here, I'm going to structure this a little bit more. Let's take a look and say, here's a query that will start to give me some metrics on min duration, max duration on particular trips, and overall how many trips were made on that route. So now I've got some characterization of the routes in aggregate. Okay, let's take and build up a graph out of this. We'll create basically node RDD to describe the different stations, and we're going to apply the station map that I had before. And then we'll create basically group by key. This is actually a good instance of using group by key. Usually you want to use a different way to do that, but group by key in this case works. I'm going to create an RDD to describe the edges between the different stations. And I'm going to basically roll those up and take a look at the median time between. Get a distribution, but also get the median. And once I've got that node RDD and that edge RDD, then I'll take and compose it into a graph, like we did before. We have a graph G. Once I've got the graph, we'll run PageRank. And so this gets back to the question. With Pregel in Spark, running PageRank is just the one call. I'm going to tell it a convergence factor. And the result of that, the vertices that come out of this are the different ranks for the different routes. So this is interesting because now I can take a look. Let me overlay this with a case class, and I'll set it up so I can do some queries. If we start to look, then we find out, aha. So the really popular nodes in this graph, Lincoln Memorial, is probably the most popular tourist attraction in Washington, D.C. And that pops out of PageRank right there. Jefferson Memorial is probably the second popular, and on. You can kind of see. So that's interesting. So PageRank is one way to get into this. Columbus Circle is a very popular part of the city. You cross through there a lot. So I wanted to show what this would look like. Let's see, grab that a little bit. So I've got Columbus Circle. It has a rank of a certain value, but it has ID 38. I want to find its ID. And I happen to know that Columbus Circle going over to 8th and F Street in Northeast. So that's a popular commuter route there for people in the city. So I'm going to take a look and pull the IDs then for both those stations. So I've got 38 as Columbus Circle, and then I've got 8th and F here. So now what I'm going to do is take and run Dijkstra again on this graph. And so we're going to tie the node that is of interest is 38, that's Columbus Circle. And then we're going to take a look at the other routes that feed in there. We're going to take a look at what is the optimal route and what's our projection on how much it'll cost. What's the median duration time? So if I do this, I'll come through and I find out that node 286, coming back here, 286 is 8th and F Northeast. Turns out that is right here. I'll collect it. So it comes out to being about 3.8 minutes to do that route, at least based off of what the data tells us. And if you look back here, Google is telling us it's a 3-minute trip by bicycle. So this is a way of being able to take a lot of data that we just dug up about bike trips, and we can start to approximate Google directions and what the estimate for travel time is for them. You can imagine if we had smartphones from people walking around the city, we could probably find out what it takes to go in a car versus walking. You'd have to do some segmentation, but you could use k-means clustering to do that. Okay, so that's a way of doing some work with both MLlib, some comparisons about different models, as well as building a graph to represent some estimates on this data set. Like I say, there's also geospatial data here. If you take a look at the coordinates for the stations, there's a lot of interesting time series to see, how long it takes to ride your bike in the snow versus not snow. So if you want to work more with this data, this is all open source. I think I have one other quick section here before we wrap it up. And that's a big picture. I know that we had some other work on approximation algorithms, but I'm going to throw an idea out here that's very controversial. So maybe I'm wrong. But in my view, the statistics, now I'm going to put out a caveat that what Andrews just showed about using Bayesian statistics, I'm a big fan of that. I love using Bayesian statistics and probabilistic methods like MCMC and probabilistic programming. I'm very interested in that. But when I look at the frequentist statistics, over the past 200 years, there's been this big emphasis on defending what you're able to show about the data, as opposed to having high-quality prediction. And a lot of this was based off of having goodness of fit tests and p-values. Have you seen that Nature magazine doesn't allow you to use p-values anymore? Anybody else seen that? It was a recent change. So there have been problems with this approach. But for 2 centuries, that's how we went. That view of frequentist stats and defensibility really led to a lot of batch window. It's a lot of the emphasis on batch windows. If you roll the clock back, before then, there was a lot of interesting work on probability, and Anders was talking about this. But if you haven't seen it, I highly recommend. There's this one gentleman, Philippe Flageolet, who unfortunately passed away a few years ago, but he had done a lot of the pioneering work in this out of INRI. And there's a good summary of this. Ilya Katsov had a nice post to describe it. And the idea is very simple. If we get away from looking at batch windows and looking at variance and goodness of fit tests, if instead we leverage the probability side of this in analyzing the data, then what Ilya is showing here is that you can make a trade-off. If you're measuring a metric in your data, you can trade off the error bounds. And for instance, here, he's showing that if you give plus or minus 4% error bounds on your metric, you can trade off 2 orders of magnitude of how much memory it takes to compute that. Now, if we're talking about streaming data, like Spark Streaming or Flink or others, being able to get your compute all into memory is actually a big deal. So here's a nice tool to be able to, number one, cut down the resources required, and number two, we're going to approximate anyway for most of the big data stuff. And so we, number three, can get rid of the batch windows. So anyway, I highly recommend, I've got listings there for Ilya Katsov and others talking about this. At Twitter, there's a catchphrase. They say, hash, don't sample. And this is how they build architectures. And so, again, this is about using approximation. One of the things, we mentioned monoids earlier. This is where leveraging languages like Scala with its type safety comes in very handy, because we can actually use abstract algebra and strong typing to create kind of containers for the business logic that we're applying to the data. And we can get a lot better parallelism and a lot better efficiencies by doing that, especially when we're doing approximation algorithms. I'll show an example. So here's, I'm sure, I know that Jeff Ullman had gone through a lot of these, but like Sketch, Countman Sketch is a way of doing frequency summaries, leaderboards if you're doing gaming, or fraudsters if you're doing anti-fraud. Hyperlog is a way of counting. Bloom filters or set membership. Jeff had shown about minhash and LSH for set similarity. Streaming quantiles are important, because a lot of times if you're building, say, an anti-fraud model, you have to look at some kind of quantile, maybe purchase velocity. And so this is a way of getting rid of the batch window and doing that all in stream. I've got links up there, but some of these are implemented in Spark directly. They're part of Spark streaming, especially like Countman Sketch and Hyperlog. Others come in as libraries. I'll point to a really great talk by Avi Bryant. He had created DoubleDB, which Twitter acquired, and his team had built out a lot of infrastructure. Nathan Mars, who created Storm, was one of the young engineers working for him. Avi Bryant's now at Stripe, but he had a great talk about why you want to use abstract algebra for analytics. And the thing is this, that if you're streaming a lot of data through a pipeline, if you have the right kind of math on your functions and you have strong typing, because of associativity, the grouping of your data doesn't matter anymore. Because of commutativity, the ordering of your data doesn't matter. You don't have to stop and take a batch window and sort your data first before you analyze it. And number three, if you've got monoids and you've defined what your identity values are, then you can look at a big sparse matrix and ignore all the zeros. If it's just numbers, ignoring the zeros is trivial. But if you've got a big sparse matrix of customer profiles, it's non-trivial. So this is a really great way to approach streaming, is to leverage the math and leverage the type safety. Oscar Boynkin was one of the research partners for Avi Bryant. He's still at Twitter, one of the lead data scientists, and he puts it very well. Lack of associativity increases latency exponentially. So if you don't have the associativity in your API, then you're going to see things like loops being used as opposed to computations in parallel. Whether you're working in Spark or Scalding or Flink or wherever, these are very important. And this is what Oscar means, is that if you take a set of numbers, a collection, and just go through a loop, it'll cost you n, order n. But if you actually parallelize this and run it on a cluster, it'll cost you order log n. And so that's an exponential difference. And what's more is that if you if you take and look at these approximation algorithms, generally speaking, you can describe them as combinations of a write function and a read function that are containerized in monoids. And so they use this analysis to be able to build a library called AlgeBird, which I highly recommend. But again, this is where the type safety and the abstract algebra come together for very, very good efficiency at scale. So, you know, until a couple of years ago, I had a hard time in abstract algebra when I was in grad school. I will admit that. And I wish I'd had this diagram. But basically, if you've got a function that has it's a binary associative operation and it has closure, and then that'll be a semigroup. And if you can define an identity element, it's a monoid. And if you have an inverse, then you've got a group, on and on. The more that you can describe, then the more that you can let the compiler leverage these properties. And so AlgeBird is a way of basically having libraries for these such that the compiler doesn't care what logic is inside. It just knows the mathematical properties. It's kind of like containers for business logic. And here's some really great ones. One of the ones I like the best is Titus Brown, and he's been doing genomic sequencing with approximation algorithms because they get so much better speed out of this. They're using such large data. But there's a bunch of others. You see actually Jeff Ullman's name on this. And Algebra is the one I point to. So if we have a moment, I can show Spark. I can do a demo. Well, I don't know if I guess this would be just one last thing I'd show about it. I've got some code here if you want to run it. I've got some examples. But I know there'd been other examples earlier of doing streaming apps. So I wanted to show this one thing. Here's a Python version of Spark Streaming. And I've got it in the slides here, but I've got it on GitHub if you want to check out. And here's the same code that's done with checkpoints, like we were talking about earlier, but also with update state by key. And so the difference between this is that we usually think of Spark as having immutable data, but by using update state by key, then we start to manage some mutability on the data. So basically, we create a key value store in memory. It's not as elegant as what you were showing earlier, but it is somewhat of the same flavor of managing mutability and immutability. And the nice thing about it then is that you can start to apply these approximation functions in Stream to develop your metrics right there, captured in a key value store. And that's how Twitter does a lot of their, in fact, most of their analytics are done in this kind of technique. Not with Spark, but with Scalding. OK, I think we're at time, and I think that's the conclusion. So thank you very much.